All right, so these questions you are going to see in every review packet from now on. So it's not just, oh, I just need to learn this in order to do the lab. No, it's you need to do this in order to be able to succeed from now on. Okay? This isn't hard. It's a little confusing at first, and then after you do it a couple times, it begins to make sense. All right? Best thing you can do with these is to make two little charts. Water chart here, and on the other side of the page, the metal chart. And then you start reading the question. What is the most likely identity of a metal that has a mass of 20 grams? So on the metal side, M equals 20.0 grams. And is initially heated in a beaker of boiling water. That is very important. That tells you a very important thing. That tells you the initial temperature of the metal, just like yesterday. When you heated the metal for 10 minutes in boiling water, what did we assume the metal was after 10 minutes? Because of the law of conservation of energy. Yes, Alex? What is it? 100 degrees. So we now know the initial temperature of the metal is 100 degrees. Let's go ahead and just give it one decimal place in order to be consistent. The metal is immersed in 30.0 milliliters of water, just like yesterday. Remember doing this yesterday. That's important. Because the density of water is 1 gram per 1 milliliter, guess what we now know? We know the mass of the water is right? If you know the volume of the water, you know the mass of the water. It's immersed in 30 milliliter sample of water in a coffee cup calorimeter with an initial temperature of 22 degrees Celsius. What does that tell you? Well, it doesn't tell you the initial temperature of the metal, does it? It's the initial temperature of the water. The mixture of water and metal climbs to a temperature of 31.8 degrees Celsius. What does that tell you? That's the final temperature of and the metal. Remember, folks, the temperature of the water will keep increasing until it meets up with the temperature of the metal. All right. Then they give you Petit and Dulong's equation, which I'll show you in a few minutes how to use to solve this question. Okay. So, well, no. Let's focus on Petit and Dulong's equation because what they need, what this question is asking for, is the identity of this metal. Petit and Dulong's equation is atomic mass, which is something that you can find on the periodic table, is equal to the number 25 divided by the specific heat of the metal. Do we know the specific heat of the metal? No. Remember our equation. Q is equal to M times TF minus TI times specific heat. Do we know the mass of the metal? Yes. Do we know the initial temperature of the metal? Do we know the final temperature of the metal? Do we know the Q of the metal? Okay, microphone drop. We're stuck there. But then you ask the question, why did they give us all that information about water? Remember my illustration that a blind person may not be able to see you directly, but how do they see you indirectly? They feel your face. In the same way, we may not know directly what the Q of the water is, but can we find it out indirect? I'm sorry, the Q of the metal, but can we find it out indirectly by finding the Q of the water? So Q is equal to mass times final temperature minus initial temperature times specific heat. Do we know the mass of the water? Do we know the initial temperature of the water? Do we know the final temperature of the water? Do we know specific heat of water? So we have everything we need to find the amount of energy that the water absorbed. I need calculators out, moving ahead of me in order to give me numbers. What is 30.0 times 31.8 minus 22.0 times 4.18? Now, remember the blind person. Can't see directly, can see indirectly. If we know that the water absorbs a positive 1,230 joules, how much energy must the metal have given off? Same number? According to the law of conservation of energy, it is. Same sign? No. If somebody is being plussed, that means somebody must be minused. Okay, remember what our dilemma was for finding the specific heat of the metal. We had mass, we had change in temperature, we did not have Q. Do we have Q now? Ooh, all right. So a negative 1,230 joules equals the mass of the metal. The initial temperature of the metal. No, the initial temperature of the metal. Ashra, the final temperature of the metal. Okay, so these numbers, this one right here and this one right here should be the same because the metal and the water both end up in the same place. Their starting temperatures are going to be very different. Where most people make mistakes is right there in the change in temperature. Be careful. Let me stop right here. Does anyone not understand how we got those numbers? Because that's critical. If you're going to make a mistake, you'll make a mistake there. This is the water boiling, right? What was the purpose of that water? Because people get confused here. There are two waters that we're working with, right? The purpose of the boiling water was to do what? to heat up the metal to 100 degrees. That's it. That's it. That was, if we could find a different way, if we had some kind of fancy oven that I could set it at 100, I would just have you guys put it in there. Or I could set it at 75. I could just have you guys put it in there for 10 minutes. But we don't. So what's the easiest way to keep a temperature steady? Boiling water. Because water's temperature will not change until all of it has boiled away. Then the temperature of the steam can go up. But as long as there's water, that temperature is 100 degrees. The water that we are most concerned about was the water that was in the cup. That was the water that was important to us. And its initial temperature was 22, not 100. All right, gang. Algebra. You guys are all in Algebra 2, trig or up higher, or an agate. This should be something you can do. What is 1,230 negative divided by 20 divided by the difference there, which, did you notice it would have to be negative as well? This should give you a decimal. If it never, and we're going to do many of these, if it doesn't give you a decimal, you've done it wrong. Because this only works if Petit and Dulong's equation only works with metals. And metals on the periodic table, their specific heat is always below 1. So that's a quick check for yourself. If you do the algebra and the number comes out to be greater than 1, you've done it wrong. Three sig digs. Zero. 0.902 joules divided by grams Celsius. If you think about it, because you're taking joules and you're dividing by grams and dividing by Celsius. All the units are there. All right. Any questions so far? We are one step away from the final answer. You ready? Petit and Dulong's 25 over 0.902 equals 27.7. Okay? So close to 28. Look on the periodic table. Who has a mass that's close to 28? Closer to 28 than 27? It says silicon, but you see a red line, zigzag line coming down? Silicon is on the other side of that zigzag line. That's a zigzag line that separates the metals from the non-metals. Okay? So, silicon is not a metal. Petit and Dulong's equation can't work for silicon. So who is the closest metal to 27.7? You may have to do the same thing with your results tonight. That's it. That's it. What do you think? It's highly likely that somebody got lost somewhere along the way. Can I get you caught up? Raise your hand. I'm expecting somebody to be lost. Yes, Alex. Okay, because we need to find specific heat, right? Our Q equation is Q is equal to mass times change in temperature times specific heat. We have the mass of the metal. We have the change in temperature of the metal, agree? We need the specific heat of the metal. We don't have Q. Two unknowns. We need Q to find specific heat. If we find specific heat, then this magical equation of 25 divided by specific heat can help us. No specific heat, we got a big problem. So what we do is we think back at our blind illustration. We can't find the Q of the metal because we're blind. But can we want to see what happens to water? Because whatever happens to water, according to the law of conservation of energy, the opposite happened to the metal. So, do we have the mass of the water? Yes. Do we have change in temperature of the water? Do we know the specific heat of water? That's a no. Yes. So, once we plugged all those numbers in, we got the Q of the water. Yes. How did that help us? Because we reversed the sign to find the Q of the metal. So however much energy the water gained, the metal must have lost. So now that you have the Q of the metal, then it's just a matter of just doing algebra to find X. Don't tell my math teacher friends that I'm saying this. The math here is kind of elegant and beautiful, isn't it? I mean, how you can take algebra, which has it seems like it has no practical purpose at all, and use it to find something needed is actually kind of beautiful. Props to our math people, our math teachers, who every once in a while stumble upon something that is useful to us. All right? And for all of you on internet land, that was just a joke. I have utmost appreciation for our math people.